Making waves. Before the early 1800s, heat was a riddle. What was it exactly? Was it a liquid like water? It did seem to follow, but you couldn't hold it in your hands or see it. You could measure it indirectly by tracking the temperature of something hot as it cooled down, but no one knew what was going on inside the cooling object. The secrets of heat were unraveled by a man who often felt cold or fat. At the age of 10, Jean-Baptiste Joseph Fourier was a sickly, dyspeptic asthmatic as a teenager. As an adult, he believed heat was essential to health. He kept his room overheated and swathed himself in a heavy overcoat. Heat in the summer. In all aspects of his scientific life, Fourier was obsessed with heat. He originated the concept of global warming and was the first to explain how the greenhouse effect regulates the Earth's average temperature. In, in 1807, Fourier used calculus to solve the riddle of heat flow. He came up with a partial differential with a partial differential equation that allowed him to predict how the temperature of an object, such as a red-hot iron hot rod, would change as it cooled. Amazingly, he found he could solve problems like this no matter how erratically the rod's temperature varied along its length at the beginning of the cooling off process. The rod could start with hot spots here and cool spots there. No sweat for the analytical method could handle it. Imagine a long, thin, cylindrical iron rod heated unevenly in a blacksmith's forge so that it has patches of hot and cold scattered along its length. For simplicity, assume a, perfectly insulating sleeve surrounds the rod so that heat can't escape. The only way heat can flow is to diffuse along the rod's length from the hot spots to cold spots. Fourier postulated, and experiments confirmed, that the rate of change of temperature at a given point of the rod was proportional to the mismatch between the temperature at that point and the average of the temperatures of its neighbor on either side of it. And when I say neighbors, I really mean neighbors. Picture two points flanking the point we're focusing on, each infinitesimally close to that point. Under these idealist conditions, the, the physics of heat flow is simple. If a point is cooler than its neighbors, it heats up. If it's hotter, it's cooled down. The greater the mismatch, the faster the temperature evens out. If a point happens to be at precisely the average of neighbors' temperatures, everything balances. Heat doesn't flow, and the temperature of that point stays the same in the next instant. The process of comparing a point's instantaneous temperature with that of its neighbors led Fourier to a partial differential equation that's now known as the heat equation. It involves derivatives with respect to two independent variables, one of infinitesimal changes in time t, and one for the infinitesimal changes in position x along the rod. The hard part about the problem Fourier said from himself is that the hot spots and cold spots could be initially arranged high-lightly piggy. To solve such a general problem, Fourier proposed a scheme that seemed widely optimistic, almost foolhardy. He claimed he could replace any initial temperature pattern with an equivalent sum of simple sine waves. Sine waves were his building blocks. He chose them because they made the problem easier. He knew that if the temperature started in a sine wave pattern, it would stay in that pattern as the rod cooled off. That was the key. Sine waves didn't move around. They just stood here. They just stood there. True, they dumbed down as their hot spots cooled off and their cold spots warmed up, but that decay was easy to handle. It merely meant that the temperature values flattened out as time passed. As sketched in the diagram below, a temperature pattern that start out looking like the sine wave would gradually damp down to look like the solid sine wave. The important thing was the sine waves stood still as they damped. They were standing waves. So if he could figure out how to take an initial temperature pattern apart and break it into sine waves, he could solve the heat flow problem for each sine wave separately. He already knew the answer to that problem. Each sine wave decayed exponentially fast at a rate that depended how many crests, and though it had sine waves with more crests decayed faster because their hotspots and cold spots were packaged closer together, which made for more rapid exchange of heat between them and hence faster equilibration. Then, knowing how each sinusoidal building block decayed, all Fourier had to do was put them back together to solve the original problem. The rub in all this was that Fourier had casually invoked an infinite series of sine waves. He had summoned the golem of infinity with calculus yet again, and he'd done it even more recursively than his predecessors had. Instead of using an infinite sum of triangular sets of numbers, he had cavalierly used an infinite sum of waves. It was reminiscent of what Newton had done with his infinite sums of our function x to the n rex, except that Newton had never claimed that he could represent arbitrarily complicated curves that included such horrors as discontinuous jumps or sub-corners in them. Fourier was now claiming exactly that. Curves with corners and jumps didn't scare him. Also, Fourier waves arose naturally from the differential equation itself, in the sense that they were its natural modes of variation, its natural standing wave patterns. They were tailored to heat flow. Newton's paper functions had no special claim as building blocks. Fourier sine wave did. They were organically suited to the problem at hand. Although his daring use of sine waves as building blocks sparked controversy and raised knotty problems of rigor that took mathematicians a century to resolve, in our own time, Fourier's big idea has played a starring role in such technologies as synthesizer for computerized voices and MRI scans for medical imaging. String theory. Sine waves also arise in music. They are the natural modes of vibration for the strings of guitars, violins, and pianos. A partial differential equation for such vibrations can be derived by applying Newtonian mechanics and Leibnizian differentials to an idealist model of a thought string. In this model, the string is regarded as a continuous array of infinitesimal particles stacked side by side and bonded to their neighbors by elastic forces. At any instant of time t, each particle in the string moves in accordance with the forces impinging on it. Those forces are produced by the tension in the string as neighboring particles yank on one another. Given those forces, each particle moves according to Newton's law F equals ma. This happens at every point x along the string. Thus, the resulting differential equation depends on both x and t, and is another example of Weber-partial differential equation. It's called the wave equation because, as expected, it predicts that the typical motion of a vibrating string is a wave. As in the heat flow problem, certain sine waves prove useful because they regenerate themselves as they vibrate. If the ends of the string are pinned down, these sine waves that do not propagate, they simply stand still and vibrate in place. If extra resistance and internal friction in the string are negligible, an ideal string will vibrate forever in such a sine wave pattern if it starts in the sine wave pattern, and its frequency of vibration will never change. For all these reasons, sine waves continue to serve as ideal building blocks for this problem too. Other vibration shapes can be built out of infinite sums of sine waves. For example, in the harpsichords used in 1700s, a string was often pulled by a quill and drawn into a triangular shape and before it was released. Even though a triangle wave has a subcorner, it can be represented by an infinite sum perfectly smooth sine waves. In other words, it does not take subcorners to make subcorners. In the diagram below, I've approximated a triangle wave southeast on the bottom with three progressively more faithful approximations by sine waves. The first approximation shows a single sine wave with the best possible amplitude based in the sense that it minimizes the total squared error from the triangle wave, the same optimality criterion we met in chapter 4. The second approximation is the optimal sum of two sine waves, and the third is the best sum of three sine waves. The amplitudes of the optimal sine waves follow a prescription that Fourier discovered. This infinite sum is called the Fourier series for the triangle wave. Notice the cool numerical patterns in it. Only odd frequencies 1, 3, 5, 7 appear in the sine waves, and their corresponding amplitudes are the inverse squares of the odd numbers with alternating plus and minus signs. Unfortunately, I can't easily explain why this prescription works. We would have to plow too, too much nitty-gritty calculus to see where those magic amplitudes come from. But the point is that Fourier knew how to compute them. By doing so, he was able to synthesize a triangle wave or any other arbitrarily complicated curve out of much simpler sine wave. Fourier's big idea is the basis for music synthesizers. To see why, consider the sound of a note such as the A above middle C. To, to generate the precise pitch, we could strike a tuning fork set to oscillate at the corresponding frequency of 440 cycles per second. A tuning fork consists of a handle and of two metal tines. When the fork is hit with a rubber hammer, the tines vibrates back and forth for 440 times every second. The vibrations excite the air nearby. When a tine vibrates outward, it compresses the air. When it vibrates back, it rarefies the surrounding air. As the air molecules jiggle back and forth, they produce a sinusoidal pressure disturbance that our ears perceive as a pure tone, a boring and colorless A. It lacks what musicians call timbre. We could play the same A with a violin or a piano, and both would sound colorful and warm, even though they too emit vibrations at a fundamental frequency 440 cycles per second. They sound different from a tuning fork and from each other because of their distinct set of overtones. That's the musical term for the waves like sine 3x and sine 5x in the earlier formula for the triangle wave. Overtones add color to a note by adding in multiples of the fundamental frequency, in addition to the sine wave at 440 cycles a second. A standardized triangle wave includes a sine wave overtone at 3 times the frequency 3 times 440 equals 1320 cycles per second. That overtone is not as strong as the fundamental sine x mode. Its relative amplitude is only 1 over 9 as large as the fundamental, and the other odd numbered modes are even weaker. In musical terms, these amplitudes determine the loudness of the overtones. The richness of the sound of a violin has to do with its particular combination of softer and louder overtones. The unifying power of Fourier's idea is that the sounds of any musical instrument can be synthesized by an array of infinitely many tuning forks. All we need to do is strike the tuning forks with right strengths at, at the right times, and incredibly, out pops the sound of a violin or a piano or even a trumpet or an oboe, although we're using nothing more than colorless sine waves. This is essentially how the first electronic synthesizers worked. They reproduce the sound of an instrument by combining a large number of sine waves. Back in high school, I took a class in electronic music that gave me a feeling for what sine waves could do. This was in the dark age of what in the dark ages of the 1970s, when electronic music was produced by a big box that looked like an old-fashioned switchboard. My classmates and I would plug cables into various jacks and turn knobs up and down, and would look and, and out and out would come the sound of sine waves, square waves, and triangle waves. My recollection is that sine waves and had a clear, open sound like flutes. Square waves sounded piercing like fire alarms. Triangle waves were brassy. With one knob, we could change a wave frequency to raise or lower its pitch. With another, we could change its amplitude to make it sound louder or softer by plugging in several cables at once. We could add waves and their overtones together in the different combinations, just as Fourier had done abstractly, but for us the experience was sensory. We could see the wave shapes on an oscilloscope at the same time as we listened to them. You could try all this for yourselves on the internet. Search for something like the sound of triangle waves, and you'll find interactive demos that will let you feel like you're sitting right there in my classroom in 1944, in 1974, playing with waves for the fun of it. The largest significance of Fourier's work is that he took the first step toward using calculus as a soothsayer to predict how a continuum of particles could move and change. This was an enormous advance beyond Newton's work on the motion of discrete sets of particles. In the centuries to come, scientists would extend Fourier's method to forecast the behavior of other continuous media like the flutter of a Boeing 787 wing, the appearance of a patient after facial surgery, the flow of blood through an artery, or the rumbling of the ground after an earthquake. Today, these techniques are ubiquitous in science and engineering. They are They are used to analyze shock waves for thermonuclear blast, radio waves for communications, the waves of digestion in the intestine that allow nutrients to, to be absorbed and send waste products moving in the right direction, the pathological electrical waves in the brain associated with the epilepsy and Parkinson's tremors, and the congestion waves of traffic on highway, as seen in the exacerbating phenomenon of phantom jams, where traffic slows down for no apparent reason. 4 years ideas and lack of sorts have enabled all of these wave phenomena to be understood mathematically, sometimes with the help of formulas, other times through massive computer simulations, so we can explain, predict, and in some cases control or abolish them. Why sine waves? Before we leave sine waves and move on to their two and three-dimensional counterparts, it's worth clarifying what makes them so special. After all, other types of curves can serve a building blocks, and sometimes they work better than sine waves. For instance, to capture localized features like fingerprint, re- reads wavelets got the nod from the FBI. Wavelets are often superior to sine waves for many image and signal processing tasks in fields like earthquake analysis, art restoration, and authentications, and facial recognition. So, why are sine waves so well suited to the solution of the wave equation and the heat equation and other partial differential equations? The the fact is that they play very nicely with derivatives. Specifically, the derivative of a sine wave is another sine wave shifted by a quarter cycle. That's, that's a remarkable property. It's not true of other kinds of waves. Typically, when we take the derivative of a curve of any kind, the curve will become distorted by being differentiated. It won't have the same shape before and after. Being differentiated is a traumatic experience for most curves, but not for a sine wave. After its derivative is taken, it dusts itself off and appears unfazed, as sinusoidal as ever. The only injury it suffers, it isn't and it isn't even an injury, really, is that the sine wave shifts in time. It peaks a quarter of cycle earlier than it used to. We saw an imperfect version of this in chapter 4 when we looked at the day-to-day variation in day length in New York City in the year 2018 and compared them to the day to the daily changes in day length, the number of minutes of sunlight from one day to the next. We saw that both curves look approximately sinusoidal, except that the difference in daylight from one day to the next performed a wave that was shifted 3 months earlier than the data from which it came. Put simply, the longest day in 2018 was June 21st, when the fastest lengthening day was 3 months later, 3 months earlier, March 20. This is what we expect from sinusoidal data. If the length data were a perfect sine wave, and if we look at its difference not from one day to the next, but from one instant to the next, then its instantaneous rate of change, the derivative wave derived from it, would itself be a perfect sine wave, shifted exactly a quarter of a cycle earlier, back in chapter 4. We also saw why the Carter cycle shift occurs. It follows from the deep connection between sine waves and uniform circular motion. You may want to look back at the argument if it seems hazy now. The quarter cycle shift has a fascinating consequence. It implies that if we take two derivatives of the sine wave, it shifts a quarter plus another quarter cycle earlier. So, in total, it gets shifted half a cycle earlier. That means that its former peak is now a valley and vice versa. The sine wave was turned upside down. In mathematical terms, this is expressed by the formula. When the Leibnizian differentiation symbol ddx means take the derivative of whatever expression appear to the right. The formula shows that taking two derivatives of sine x amount to nothing more than multiplying it by -1. This replacement of two derivatives by a simple multiplication is a fantastic simplification. Taking two derivatives is full-block calculus operation, whereas multiplying by -1 is middle school arithmetic. But why? You may be asking yourself, will anyone ever want to take two derivatives of something? Because nature does, and it does it all the time. Or rather, our models of nature do it all the time. For example, in Newton's law of motion, F equals ma, the acceleration the acceleration a involves two derivatives. To see why, remember that the acceleration is the derivative of speed, and speed is the derivative of distance. That makes acceleration the derivative of the derivative of distance, or to put it more concisely, the second derivative of distance. Second derivatives come up everywhere in physics and engineering. Along with Newton's equation, they also star in the heat equation and the wave equation, so that why sine waves are so well suited to those equations. For sine waves, two derivatives boil down to mere multiplication by -1. In effect, in, e- in effect, the inherent calculus that made the heat and wave equations hard to analyze is no longer an issue when we restrict our attention to sine waves. The calculus gets stripping out and replaced by multiplication. This is what made the vibrating string problem and heat flow problem so much easier to solve for sine waves. If an arbitrary curve could be built from them, that curve would inherit the features of sine waves. The only hitch was the only hitch was that infinitely many sine waves needed to be added together to build up an arbitrary curve, but that was a small price to pay. This is the calculus perspective of why sine waves are special. Physics Physics have their own perspective, one that is also worth understanding to a physicist. What's remarkable about sine waves in the context of vibration and heat flow problems is that they form standing waves. They do not travel. They do not travel along the string of the rod. They remain in place. They oscillate up and down but never propagate. Even more remarkably, standing waves vibrate at unique frequency. That's a rarity in the world of waves. Most waves are a combination of many frequencies, just as white light is a combination of all the colors of the rainbow. In that respect, a standing wave is pure, not a mixture. Visualizing modes of vibration, Chladni patterns. The warm sound of a guitar and the plaintive sound of a violin are related to the vibration set up in the belly and body of the instrument, in the wood and the cavities inside where sound waves vibrate and resonate. Those vibration patterns determine the quality and voice of the instrument. That's part of what makes a Stradivarius so special. Its uniquely evocative vibration patterns of wood and air. We still don't understand exactly what makes certain violins sound better than others, but the key must be something about their modes and vibration. In 1787, a German physicist and musical instrument maker named Ernest Kaltny published an article showing a clever way to visualize these vibrational patterns. Instead of using a shape as complicated as a guitar or a violin, though he played a much simpler instrument, a thin metal plate. By drawing a violin bow across its edge. In this way, he was able to get the plate to vibrate and sing, a bit like the way you can get a half-filled wine glass to sing by rubbing your finger and around its rim. To visualize these vibrations, Courtney sprinkled a, a fine dust of sand onto the plate before he bowed it. When he struck the plate, the sand bounced off parts that were vibrating the most and settled in the parts that weren't vibrating at all. The resulting curves are now called Cal- Courtney patterns. You may have seen a demonstration of Courtney patterns at science museums. A metal plate is placed over a loudspeaker and covered with sand. Then it's driven to vibrate by an electronic signal generator. As the frequency of the sound coming out of the loudspeaker is adjusted, the plate can be excited into different resonant patterns. Whenever the loudspeaker turns into a new resonant frequency, the sound rearranges itself into a different standing wave pattern. The plate divides itself into neighbored regions that vibrate in opposite directions, bounded by another course. When the plate remains motionless, perhaps it seems odd that some parts of the plate don't move, but that shouldn't be surprising. We saw that we saw the same thing with sine waves on a string. The points when the string doesn't move are the notes of vibration. For a plate, there are similar notes, except they are not isolated points. Rather, they link together to form nodal lines and curves. These are the curves that Galtoni made manifest in his experiments. They were considered so astonishing at the time that Galtoni was invited to show them to Emperor Napoleon himself. Napoleon, who had some training in math and engineering, was intrigued that he established a contest and challenged the greatest mathematicians of Europe to explain Galtoni patterns. The necessity mathematics did not exist at the time. The preeminent mathematician in Europe, Joseph Louis Lagrange, felt that the problem was beyond reach and that no one would solve it. Indeed, only one person tried. Her name was Sophie Germain. The noblest courage. Sophie Germain had taught herself calculus at a young age. The daughter of a wealthy family, she had become entranced by mathematics after reading a book about Archimedes in her father's library. When her parents found out that she loved mathematics and was staying up late at night to working on it, they took away her candles, left her fire unlit, and confiscated her nightgowns. Sophie persisted. She wrapped herself in quilts and walked by the light of stolen candles. Eventually, her family relented and gave her the blessing. German, like all women of her era, was not permitted to attend university, so he continued to teach herself, in some cases by obtaining letter notes from the courses at the nearby École Polytechnique using the name Monseigneur Antoine Auguste Leblanc, a student who had left the school. Unaware of his departure, academy administrators continued to print lecture notes and problem sets for him. She submitted work under his name until one of the school's teachers, the great Lagrange, noticed the remarkable improvement in Monsieur Leblanc's previously abysmal performance. Lagrange requested a meeting with Leblanc and was delighted and astonished to discover her true identity. He took Germaine under his wing. Her earliest triumphs were in number theory, where she made important contributions to one of the most difficult unsolved problems in that field, known as Fermat's last theorem. When she felt she'd made a breakthrough, she wrote to the world's greatest number theorist and one of the greatest mathematicians of all time, Carl Friedrich Gauss, once more using the pseudonym of Antoine Leblanc. Gauss admired the brilliance of his mysterious correspondent, and they conducted a lively exchange of letters for 3 years. Matters darkened one day in 1806 when events threatened Gauss' life. Napoleon's army had begun storming through Prussia, and Gauss' home city of Brunswick was taken. Using the family connections, Germain wrote to a friend who was a general in French army and asked him to guarantee Gauss' safety. When word got back to Gauss that his life had been protected by the intervention of Mademoiselle Sophie Germain, he was grateful but puzzled, since he knew no one by that name. In her next letter, Germaine unmasks herself. Gauss, flabbergasted to learn that he had been corresponding with a woman. Given the depth of his insights, and recognizing all the prejudices and obstacles she must have endured, he told her that, without doubt, she must have the noblest courage, quite extraordinary talents, and superior genius. So, when she heard of the competition to solve the mystery of Chladni patterns, Germaine rose to the challenge. She was the only person brave enough to take a step at developing the necessary theory from scratch. Her solution involved creating a new subfield of mechanics, the theory of elasticity of flat, thin, two-dimensional plates, going beyond the earlier and much simpler theories for one-dimensional strings and beams. She built it on principles of forces and displacements and curvatures, and she used techniques of calculus to formulate and solve the relevant partial differential equation for Chladni's vibrating plates and the marvelous patterns they produce. But given the gaps in Germain's education and her lack for formal training, he attempted solution contained flaws that the judge noticed. They felt that the problem had not been fully solved, and they renewed the contest of another 2 years, and then another two after that. On her third day, Germain was awarded the prize, the first one ever to be so honored by the Paris Academy of Sciences. Microwave ovens. Chladni allows us to visualize standing waves in 2 dimensions. In our daily lives, we rely on the three-dimensional counterpart of Chladni patterns whenever we use a microwave oven. The inside of a microwave oven is a three-dimensional space. When you press the start button, the oven fills with a standing wave pattern of microwaves. Though you can't see these electromagnetic vibrations with your eyes, you can visualize them indirectly by mimicking what Chladni did with his sand. Take a microwave-safe plate and cover it completely with a thin layer of processed shredded cheese or anything else that will lie flat and melt easily, like a thin slab of chocolate or a sprinkling of mini marshmallows. Before you put the plate in the oven, be sure to take out the rotating turntable. That's important because you want the plate of cheese or whatever you're using to stand still to allow you to detect the hot spots. Once the turntable is out and the plate is inside, close the door and turn on the microwave. Let it go for about 30 seconds, no more. Then turn out the plate. You'll see places where the cheese had melted completely. Those are the hot spots. They correspond to antinodes of the microwave pattern, the place where the vibrations are most vigorous. They're like the peaks and, and through a sine wave, or like the places in the Chladni pattern where the sun is not, because the vigorous oscillations have shaken it off. For a standard microwave oven that runs 2.45 GHz, meaning the wave vibrates back and forth to 2.45 billion times a second. You should find that the distance between neighboring melted spots is about 2.5 inches or 6 centimeters. Keep in mind that's only the distance from a peak to a true, and hence is half a wavelength. To get the full wavelength, we double the distance. Thus, the wavelength of standing wave pattern in the oven is about 5 inches or 12 centimeters. Incidentally, you can use your oven to calculate the speed of light. Multiply the frequency of vibration listed on the oven's door frame by the wavelength you measure in your experiment, and you should get the speed of light or something pretty close to it. Here's how it will go with the numbers I just gave. The frequency is 2.45 billion cycles per second. The wavelength is 12 centimeters per cycle. Multiplying them with multiplying them together gives 29.4 billion centimeters per second. That's pretty close to the accepted value for the speed of light, 30 billion centimeters per second. Not bad for such acute measurement. Why microwave ovens used to be called radar ranges? At the At the end of World War II, the Raytheon Company was looking for new applications for its magnetrons, the high-power vacuum tubes used in radar. A magnetron is the electromagnetic analog of a whistle. Just as a whistle sends out sound waves, a magnetron sends out electromagnetic waves. These waves can be bounced off an airplane overhead to detect how far away it is and how fast it's moving. Nowadays, radar is used to track the movement of everything from ships and speeding cars to fastballs, tennis serves, and weather patterns. After the war in 1946, Raytheon had no idea what it was going to do with all the magnetrons it had been manufacturing. An engineer named Percy Spencer noticed one day that a peanut cluster bar in his pocket had turned into a GUI. sticky mess while he was working with a magnetron. He realized that the microwaves it emitted could warm food very effectively. To explore the idea further, he tried pointing a magnetron at an egg, and it got hot. It exploded in someone's face. Spencer also demonstrated that he could make popcorn with it. This connection between radar and microwaves is why the first microwave ovens were called radar range. They were not a commercial hit until the late 1960s. The first microwave ovens were too big, almost 6 feet tall, and extremely expensive, costing the equivalent of tens of thousands of dollars in today's money. But eventually, microwaves become sufficiently miniaturized and cheap enough that ordinary families could afford them. Today, at least 90% of households in industrialized countries have them. The story of radar and microwave ovens is a testament to the interconnectedness of science. Think of what went into them: physics, electrical engineering, material science, chemistry, and good old serendipitous invention. Calculus played an important part too. It provided the language for describing waves and the tools for analyzing them. The discovery of the wave equation, which started as an outgrowth of music in connection with vibrating strings, was ultimately used by Maxwell to predict the existence of electromagnetic waves. From there, it was a short hop to vacuum tubes, transistors, computers, radars, and microwave ovens. Along the day, Fourier's methods were indispensable, and as we are about to see, his techniques played a role in the discovery of a new use for higher energy electromagnetic waves. These much more energetic waves were discovered by accident at the turn of 20th century. No one was sure what they were. In honor to the unknown in mathematics, they were they were named X-rays. X-rays, computer tomography, and brain imaging. Microwaves are good for cooking, but X-rays are good for seeing into our bodies. They allow non-invasive diagnosis of broken bones, skull fractures, and curved spines. Of curved spines. Unfortunately, the traditional X-rays captured on black and white film are insensitive to subtle variations in tissue density. This limits the usefulness for examining soft tissues and organs. A more modern form of medical imaging, called CT scanning, is hundreds of times more sensitive than conventional X-ray films. Their precision has revolutionized medicine. The systems for computerized and T stands for tomography, meaning the process of visualizing something by cutting it into slices. A CT scan use a CT scan uses X-rays to image an organ or a tissue one slice at a time. When a patient is placed in a CT scanner, X-rays are sent through the patient's body at many different angles and recorded by a detector on the other side. From all that information, from all those views at different angles, it's possible to reconstruct much more clearly what X-rays pass through. In other words, CT scan is not just a matter of seeing, it's a matter of inferring, deducing, and calculating. Indeed, the most brilliant and revolutionary part of CT is its use of sophisticated mathematics. With the help of calculus, Fourier analysis, signal processing, and computers, the CT software inverts the property of the tissue, organ, or bones, or bone to which the X-rays pass, and then generates a delta picture of that part of the body. To see how calculus plays a role in all this, first we need to understand what problem CT solves and how it solves it. Imaging. Imagine firing a beam of X-rays to a slice of brain tissue. As the X-rays travel, they encounter gray matter with white matter, possibly brain tumors, blood clots, and so on. These tissues absorb the X-rays energy to a greater or lesser degree depending on the type of tissue it is. The goal of CT is to map the absorption pattern in the whole slice. From the information, CT can reveal where tumors or clots may be. CT doesn't see the brain directly. It sees the X-ray absorption of pattern in the brain. The math works like this. As an X-ray travels through a given point in the brain slice, it loses some of its intensity. This loss of intensity is like what happens when ordinary light passes through sunglasses and becomes less bright. The complication here is that there is a sequence of different brain tissues along the X-ray path. So the tissue act more like a sequence of sunglasses, one in front of another, one of all of different opacities. And we do not know the opacity of any of the sunglasses. That's what we're trying to figure out. Because of this invariably in the absorption properties of the different tissues, when the X-rays emerge from the brain and strike the X-ray detector on the other side, their intensity has been reduced by disparate amounts along the way. To compute the net effect of all of these reductions, we have to figure out how much the intensity was reduced step by infinitesimal step as the X-rays travel through the tissue and then combine all the results appropriately. This computation amounts to an integral. The appearance of integral calculus here shouldn't come to as a surprise. This it's the most natural way to make this very complicated problem more tractable. As always, we appeal to the infinity principle. First, we imagine chopping the X-rays path into infinitely many infinitesimal steps. Then we figure out how much their intensity and not attenuates with every step. And finally, we put all the answers back together to compute the net attenuation along the given line of travel. Sadly, having done this, we've obtained only a single piece of our information. We know the total attenuation of the X-rays only along the particular path that X-rays followed. That does not tell us much about the brain slice as a whole. It does not even tell us much about the particular line the X-rays traveled on. It just tells us the net attenuation along the line, not the point-to-point pattern of attenuation along it. Let me try to illustrate the difficulty by analogy. Think about all the different ways we could add up numbers to make 6, just as the number 6 can result from 1 plus 5 or 2 plus 4 or 3 plus 3. The same net attenuation of X-rays could result from many different sequences of local attenuations. For example, there could be high attenuation at the beginning of the line and low attenuation at the end. Or it could be the other way around. Or there could be a constant medium level of attenuation the whole way through. We have no way of discussing distinguishing among these possibles from just one measurement. However, once we recognize the difficulty, we can immediately see how to solve it. We need to fire X-rays along many different directions. That's the heart of computerized tomography. By firing X-rays from multiple directions to the same point of tissue and then repeating the measurement of many different points, we should in principle be able to map out the attenuation factors everywhere in the brain. This is not quite the same thing as looking at the brain, but it's almost as good because it provides information about which types of tissues occurs in which brain regions. The mathematical challenge then is to reassemble the information obtained from all the measurements along lines with a coherent two-dimensional picture of the whole brain slice. This is where Fourier analysis came in. It allowed a South African physicist named Alan Cormack to solve the reassembly problem. Fourier analysis entered because there was a cycle lurking in the problem. That cycle was the cycle of the lines, all the directions along which the X-rays could be fired, etched on into a two-dimensional slice. Remember, the cycle I always associated with sine waves, and sine waves are the building blocks of Fourier series. By writing the assembly problem in terms of Fourier series, Cormack was able to boil a two-dimensional reassembly problem down to an easier one-dimensional problem. In effect, he got rid of the 360 degrees of possible angles. Then, with great prowess in integral calculus, he managed to solve the one-dimensional reassembly problem. The upshot was that, given the measurements along a full cycle of lines, he could deduce the properties of the tissue inside. He could infer the absorption map. It was almost like seeing the brain itself. In 1979, Cormack shared the Nobel Prize in Physiology or Medicine with Godfrey Hounsfield for the development of computer-assisted tomography. Neither of them was a medical doctor. Cormack developed the Fourier-based mathematical theory of CT scanning in the late 1950s. Hounsfield, a British electrical engineer, invented a scanner in collaboration with radiologists in the early 1970s. The invention of the scanner provides another demonstration of the unreasonable effectiveness of mathematics. In this case, the ideas that made CT scanning possible had existed for more than half a century and had no connection whatsoever to medicine. The next part of the story began in the late 1960s. Hounsfield has already tested a prototype of his invention on pigs' brains. He was desperate to find a clinical radiologist to help him extend his work to human patients, but one doctor after another refused to meet with him. They although he they all thought he was a crackpot. He knows soft tissues couldn't be visualized with X-rays. A traditional X-ray of a head, for example, showed the skull bones clearly, but the brain looked like a featureless tumor, hemorrhages, and blood clots weren't visible despite what Hounsfield claimed. Finally, one radiologist agreed to hear him out. The conversation didn't go well. At the end of the meeting, the skeptical radiologist handed Hounsfield a jar containing a human brain with a tumor in it and challenged him to image it with his scanner. Hounsfield soon broke back images of the brain that pinpointed not only the tumor but also area of bleeding with it. The radiologist was stunned. Word spread and soon other radiologists came on board. When Hounsfield published the first computerized tomographs in 1972, they shocked the medical world. Radiologists could suddenly use X-rays to see tumors, cysts, gray matter, white matter, and the fluid-filled cavities of the brain. Ironically, given that wave theory and Fourier analysis began with the study of music, at a key moment in the development of computerized tomography, music proved indispensable again. Hounsfield had his breakthrough ideas in the mid-1960s when he was working for a computer called Electric and Musical Industries. He had first worked on image, radar, and guided weaponry, and then he turned his attention to developing Britain's first all-transistor computer. After that smashing success, Eamon decided to support Hounsfield and let him do whatever he wanted for his next project. At the time, Eamon was flush with money and could afford to take risks. Their profits had doubled after they signed a band from Liverpool called the Beatles. Hounsfield approached management with his idea of imaging organs with X-rays and EMIs. The deep pockets had helped him take the first step. He came up with his own approach to solving the assembly problem in the mathematics, unaware that Cormac had solved it earlier. And Cormac in turn did not know that a pure mathematician named Johann Radon had solved it 40 years before him with no application in mind. The quest for pure mathematical understanding had given CT scanning the tool it needed half a century ahead of time. In Cormac's Nobel Prize address, he mentioned that he and his colleague Todd Quinto had looked into Radon's results and were trying to generalize them to 3 and even 400 and even 4-dimensional regions. That must have been hard for his audience to fathom. We live in a 3-dimensional world. Why would anyone want to study a 4-dimensional brain? Cormac explained. What is the use of these results? The answer is that I don't know. They will almost certainly produce some theorems in the theory of partial differential equations, and some of them may find application in imaging with MRI or ultrasound, but that it's by no means certain. It is also beside the point. Quinto and I studying these topics because they are interesting in their own right as mathematical problems, and that it's what science is all about.